Okay, so today is Wednesday, November 11th, and this is ECE641, model-based imaging. And today we're going to hopefully finish up the material on the EM algorithm. Actually, let me get my paper notes out. And so I want to do the stuff on sufficient statistics and the EM algorithm. And then we'll maybe start up on the Markov chains. There's a chapter in there on estimation, but I usually skip that. I mean, it's useful information, but we can only cover so much. So let me finish up the EM algorithm. So basically, okay, let me just kind of cover again what happens. So you have an E step and an M step, okay? You have an E step. The E step is expectation, and the M step is maximization. The maximization refers to the maximum likelihood, okay? And I think maybe the most classic example of how you do this is let's see. Is clustering for Gaussian mixtures. So this is sort of a conceptual view of the algorithm. This is the actual algorithm, although maybe it should show a repeat, okay? And so the E step, for the E step, you calculate these probabilities. So the probabilities, these probabilities P, right? They're the probability that the nth sample falls into class M. In this day and age of deep neural networks, I think maybe that's easier for people to understand, because the deep neural networks always generate, it's very common for them to generate these softmax outputs, they call them. I'm not sure it's the greatest name, but that's what they call them. And where the M is like the softmax, it's the classification value, and the N might correspond, well, and here it's time, so for each time point. But in, say, a convolutional neural network, if you work with those, this might be the position in the image. So at every position, it gives you a different class probability. So for every position, you get a different probability. That's a matrix. And a matrix you can store, or what they call a tensor in deep learning. I feel like by giving these analogies to deep learning, for some reason I feel like the students know about deep learning osmotically, okay? But maybe that's not true. Certainly we're not really covering it in this class, but you know, so you have an array, and the array is in time. Okay, so this is n equals 1 through n, okay? And then, but for each time, you have class this way. So it's m equals 0 to m minus 1, okay? So in this case, it would be 2, because it would be 3 minus 1. And you fill this array in with these probabilities, p and m. And the way you do it is you calculate the posterior probability that sample comes from that class. And that's easy enough to do, because you just, this thing here, this is the conditional probability of y given the assumption that it's from class M, all right, times the probability that it would come from class M. So this is just Bayes' rule, okay? And the thing on the bottom looks complicated, but in some sense it's really simple. The thing on the bottom you can almost ignore, because it's just a multiplying, it's just a scaling constant. And why the scaling constant is just chosen to make sure that this is a probability density in M. So it has to sum to 1, right? It That's the sum of 1. So that's all this is. The thing on the bottom is just ugly and confusing. But what's really important is the thing on the top. Because you fill in the table with the thing on the top, and then you normalize the columns to sum to 1, okay? Right? So that can be viewed as the so there's sort of two steps. The regrouping and the re-estimation. So you're regrouping the samples, you're putting them into the buckets, okay? Except for the buckets are fractional. So you don't, each ping pong ball doesn't just go into one bucket. It's like you take the ping pong ball and you cut up into pieces and you put it partially into the different buckets, okay? So that's what this P does, and that's the E step, okay? Then once you do that, then you go to the M step. So now you take all the stuff in the different buckets and you do the calculation of the maximum likely estimates to the parameters. So you have to estimate the parameters for each of what you might call the classes. Right, so there are M classes. In this case I'm showing here, there are 3 classes. For each of the 3 classes, you have to re-estimate the parameters. So there's a regrouping and a re-estimation. The re-estimation is the M step. So the re-estimation, so now what happens, these are kind of obvious, I think. I don't know, somebody might look at this and they'd say, whoa, that's obvious. No, okay, well, I admit, there's a lot of symbols and stuff up here, but if you think of them in a logical way, they kind of make sense. They say, I'm not a very good chess player. Are there any good chess players in the room? Sometimes, people are like really good chess players, okay? I've had some friends that were good chess players. And, they say, when I play chess, what I do is I just stare at the board for like 15 minutes trying to figure out what to do, okay? And then I move some piece, and then my pawn takes me, okay? Because I'm confused. But for really good chess players, they see the chessboard as a unit, okay? They see a position, right? And it's the same thing when I'm looking at these equations. I don't really see the individual symbols, okay? I see it as a unit, okay? As a unit. And if you look at it as a unit, it's actually kind of obvious, right? So, because the first thing is just calculating the number of samples in each that fell into each of the classes. So to calculate the number of samples in the first class, you just sum, right? Because if it was a discrete case, you'd have a 1 here if that sample fell into that class. So you just count the number of things that fell into that class. Now it's fractional, so you're going to sum up, and instead of giving a discrete count the number of things that fell into that class, you'll get a fractional sum, okay? The next thing, then you just normalize that by n, and it gives you the probability. So that is the observed rate. This is like, I hesitate to even use the word, this is like the election, okay? Because you're counting the number of people that fall into each class, okay? Right? You just, if you're trying to figure out how many people like vanilla ice cream, you ask, it's like polling, okay? You ask everybody, do you like vanilla or chocolate? Okay, blah, blah, blah. You go through, you sum up the number of people who said vanilla, you divide by the total number of people, that's the fraction that like vanilla ice cream, right? It's very obvious. So you divide this by that, and it gives you the percent, and that's an estimate at the rate at which vanilla ice cream lovers occur, okay? Then the next thing here, this is now computing the expected value of the observation y for that class. So if you didn't have this, that would be just the average, right? But this is a weighted average where you weight by the probability that it's in a category. Now remember, you're summing over n, right? So what you're doing is, okay, so if you fix m, then you'd have a sum over n of this p of n, right? But this thing here is exactly what happens if this is just shorthand notation, because if you take that, this is weight, this is a weight. So basically, this is a weight, this is the dividing by the sum of the weights. So this is going to be a weighted average. It's just a weighted average for each class. But you have to do it for each m, because for each m, you compute a weighted average of the y's for that class, okay? Does that make sense? Are there any questions about that? And then for the sigma, you plug in that weighted average here for the mean, and you square this. Now, why does it come out exactly like this? I mean, this is like proof by intimidation, but you should never be you should never allow intimidation to prove anything, okay? You just put a bookmark in your brain and go say, well, if I really want to be sure, I have to go back and check it. And how would you go check it? You'd go back to the Q function, okay, and you'd maximize the Q function, and it would turn out that this was the answer. But it seems pretty plausible that this is correct, because you had done the case of estimating the mean, the maximum likely estimates of the mean and variance for the case where you just, oops, what's going on? For the case, why did that turn off? That's kind of weird. For the case where you just had like independent guessing random variables with fixed mean and variance, right? And you know what the formula is for that. The only thing that's a little funky here is that you, instead of dividing by nm minus 1, you divide by nm. Why is that, by the way? Yes, because it's the maximum likelihood. And that's what we're doing. We're maximizing Q, right? So we're computing the maximum likelihood, effectively. And this is the term you get for the maximum likelihood case. So that's why we stick with the maximum likelihood, because if you start putting n minus 1, it gets all messed up, because n could here be even less than 1, okay? So it doesn't work. But it works as long as you stick with maximum likelihood. That's why you might have said, well, in the beginning, why did we use maximum likelihood? You told me that the maximum likelihood estimate of the variance was uniformly inferior to the minimum mean square unbiased estimate, which is the same thing, but you divide by n minus 1. Well, the reason is that formula doesn't go through in these more esoteric cases. So you do it like this, okay? Because it comes out better. And asymptotically, it's the same. All right? So that makes sense? You got this? But the problem is now we had to do a lot of calculations to get this. So are there any questions about this? So you don't seem to like my chalk philosophy. And this is what it looks like. You have a bunch of samples. You take each sample and you divide it among the different buckets. So the big circles are the buckets, right? Or the clusters is what I'm going to call them. And the little circles are the samples. So each sample you divide among the buckets. Then for each bucket, you recompute the values of the parameters. The parameters for that bucket are pi, that determines the rate at which the bucket occurs. Mean, the average for the samples in the bucket, and sigma, the standard deviation in this case, okay? And now the problem is once you have these parameters, then your estimates of these p's change, so you have to keep iterating. Now why is it that the iterations, why would you expect the iterations to converge? Or why is it, what's the justification for the fact that, so you need, when you compute about a set of parameters here in the re-estimation, those parameters are different than the parameters used to compute the p's, right? Initially. So now if you go and recompute the p's, you'll get different values, right? And then with those new values of the p's, you'll compute new values of these parameters. So there's a chicken and egg issue, right? Every time you re-estimate the parameters, you'll get a new grouping. Every time you get a new grouping, you'll get new parameters. So it seems like, well, are you ever going to converge? I mean, what's going to happen? What's the justification for that iteration being a good thing to do? What happens every time you iterate that process?
It monotonically increases the likelihood, and the likelihood is bounded above.
Yes. Okay, it monotonically increases the likelihood. Every time you iterate this, it's not just ad hoc. I mean, you could have just said, well, let's just do this. And maybe that would be okay. Sometimes just doing goofy, heuristic, ad hoc things works great, okay? And you just do it, and you go, well, and you don't worry about it too much. But the justification here is that each time you iterate this, you're increasing the likelihood, okay? You're increasing the log likelihood. You're decreasing the negative log likelihood, right? So if the likelihood is bounded above, then something's got to give, right? I mean, it just can't go, something's got to give. At least the estimates of the parameters, I don't want to get too hyper-technical because I'll confuse people, but you would expect the parameters converge. Actually, it's not technically the case that it has to, but you would sort of expect that in a practical situation. However, I'll just point out, don't listen if this disturbs you, is that it doesn't necessarily converge because the likelihood is not bounded above for this clustering problem. Why? Because the problem is that, let's say you just have one point, say 0, okay? So okay? And you have a cluster. Your cluster is that mu, say 1, I don't know, is at 0, and sigma 1 squared is epsilon, okay? And you let epsilon go to 0. Then the log likelihood goes to infinity. Why? Because if you make the distribution more and more peaked, around 0, the probability of that event gets higher and higher and higher. So that's sort of an instability when you're doing clustering for this kind of thing, that you have to be careful. You're not allowed to like have a cluster with only one sample in it and then let the probability get larger, 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 because there's something wrong about that, right? There's a problem with order identification, basically. I mean, because, I mean, do you see what the problem is intuitively? So usually when people have clustering algorithms, they exclude the possibility that a cluster only has one sample, and they limit. Maybe you can also put a lower bound on sigma to make sure that you don't have, because there's basically local minimum that go to infinity, or well, they're not local minimum, they're global minimum. But they're sort of aberrations, right? So you have to guard against those things. Okay, now, and it talks about that in the convergence. Now, okay, exponential, by the way, could somebody look at the screen on the camcorder and just make sure, is there decent contrast so you can actually read the text on the screen? Or does it look really hopelessly bad?
It's really hard to see.
I don't know how to set it in any other way. It's funny, at the beginning of the class, I think the auto exposure settings might have changed.
It might be just, it needs to be tilted up a little more even, because if it's got more
I think it's the auto exposure. Hold on, let me see if I can. It's in auto exposure. Auto, is that any better? Okay, we're going to assume that's better. Okay.
That's much better, yeah.
It's not better?
It is much better.
Oh, it is better. Okay,
Yes.
good. I touched that little button there. This is the problem. Engineers hate reading instructions. Okay. I should read the instructions, but as a matter of principle, I don't want to. Okay, so Okay, so exponential distribution. So is any distribution, so this is a sufficient statistic, okay? A statistic is sufficient if you can write, so the statistic here would be t. A statistic is any function of the data. The data here is y, okay? Theta is the parameters. So t of y is the statistic. So if you can write the probability density function in this form, then you say that t is a sufficient statistic for theta, okay, given this distribution. Now, a special case of a sufficient statistic, and this is just a simple little proof that says the maximum likelihood estimate, in particular, can be written as a function of the sufficient statistic. So, okay, so there's going to be some function of the sufficient statistic. Now, to illustrate it, if we define like S, if we define B and S, so we have a bunch of Gaussian random variables, IID, and their distribution is n 0 sigma squared, right? Then you can write the probability distribution in this form, okay, with some manipulation. And so where B and S, B here is the sum of the y's, and S is the sum of the squares of the y's. So the B and S, so let's say you have 1,000,000 samples. B and S is so Y is a 1,000,000 dimensional. So if you're going to store it on the computer as floats, you'd have to take up a million, well, it's actually 4 bytes for a float, so it would be 4 million megabytes, okay? But if you're going to store S and B as doubles, then you'd only have 16 bytes, okay? So computing B and S saves a lot of computing, a lot of memory and storage, okay? So we call it a sufficient statistic. Now, once you have B and S, you can calculate the maximum likelihood estimate as a function of B and S. And let's see, the function of B and S is what? Oh, okay. Well, Well, the function of B and S is going to be what? It's the. I guess I can erase this. For this problem, now what's going to end up happening is people won't be able to see the blackboard. So B is the sum of the squares. So what will happen is that mu is just equal to B over N, right? Mu is equal to B over N because B is the sum of the measurements. So that would be not mu, that would be mu hat, the estimate. And then sigma squared hat is going to be equal to what? Well, it would be S over N if the things were zero mean. But if they're not zero mean, then you have to correct that by taking mu squared, right? So it's mu hat squared, right? So it's going to be B squared over N squared, I guess. Does that look right? It must be. Where is it? Yeah, B squared over N squared. Yeah, it's in the notes. B over N squared. That is why it looks unfamiliar, because I wrote it that way in the notes. Okay? So is everybody clear on that? So you can write, this is the function of the statistics. This is the function of the statistics that produces the maximum likelihood estimates of the sufficient statistics. The sufficient statistics here are S and B. Are sufficient statistics random variables? Well, it's a little unclear because I've been a little bit, sloppy often, but the answer is yes, because they're functions of the data, and the data is assumed to be a random variable. So the sufficient statistics are random variables because they're dependent on the data. The unknown parameters, mu and sigma here, are assumed to be numbers, not random. But their estimates are random because they're functions of the data, okay? So now you have an exponential family. For an exponential family, you assume that you can write the probability distribution like this. So in particular, okay, here, this is, a t here is now a vector valued function of y. So it's a vector value function. It's not necessarily a linear function of y, but it's a vector value function. So in this particular case, t of y is equal to y. It was b and s, okay? And we know b was the sum of the y's, and s was the sum of the squares of the y's. So that's what t is, and eta is some function of the thetas. So the question is, if you can write the distribution in this form, now there's an important constraint here, which is that this is an inner product, so it means it's linear. Inner products have to be linear. So that's got to be true. Well, I mean, if you go back and look at this expression over here, you can see that it's true, because this is s, and this is a function of the parameters. A 1 over 2 sigma squared is a function of the parameters, and mu over sigma squared is a function of the parameters. So this is showing, and this is just a constant. So here you can see that you can express this as an exponential of an inner product between a vector of sufficient statistics. The vector of sufficient statistics is b and s, times a vector of a function of the parameters. Okay, so here eta of theta is equal to what? It's going to be, for that particular example, it's minus 1 over 2 sigma squared, and this is mu. Oh, I wrote it in the wrong order. It's mu over sigma squared, and it's minus 1 over 2 sigma squared. So you multiply this by that. B gets multiplied by mu over sigma squared. And then S gets multiplied by minus 1 over 2 sigma squared. And then they get added, because that's what it means to take an inner product between two things. Is everyone clear on that? So because I can write, are you clear? Do you have any questions about that? Okay, so because I can write the probability distribution in this form as the inner product between the function of the statistics and a function of the parameters, then it meets the requirements associated with an exponential distribution. And in that case, we say that these statistics are the natural sufficient statistics for the exponential distribution. So a few things. First of all, we say that it's an exponential. It's not actually an exponential distribution, okay? It's an exponential family of distributions, okay? Because an individual distribution can't really be exponential, I guess. Well, maybe it can. Maybe you just say, okay, for this, I mean, in that case, omega's n is sort of a degenerate case, okay? The whole concept of an exponential family is that it's a collection of distributions parameterized by a parameter theta, okay? And for that family of distributions parameterized by theta, if it meets these constraints, if it can be written this way, then we say that T is the natural sufficient statistic for that family of distributions. So if I say Gaussian distributions, I mean like the family of Gaussian distributions parameterized by the mean and the variance. Or if I say gamma, I mean, every family of distributions has some set of parameters. By the way, if you go to Wikipedia, they always list these out, okay, for the different families, okay? So you clear on that? Now, what's less possibly obvious is, okay, then, it would be truly perverse if it wasn't the fact that natural sufficient statistics were sufficient statistics. Okay, it's true, okay? It's also true that natural sufficient statistics for exponential distributions are sufficient statistics. You have to go back and check that we've met the constraint of the definition of a sufficient statistic. But it would be truly weird if you had used that name and it wasn't. Okay, and so since it's a sufficient statistic, I can write the maximum likelihood estimate as a function of those natural sufficient statistics. And this just shows that it tells you here it is. Okay, I did it on the blackboard and my answer is correct. So it tells you here, it shows as an example exactly how you can do the decomposition. Okay, now maybe what's, okay, so that's all good. So example, this is blah, 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 blah. I kind of did this already. This is the generalization to the multivariate case. Oh, that's maybe important. So here, y is a vector. So the observations are vector valued. And instead, they have a mean, which is a vector, and then they have a covariance, which is a matrix. It's a positive definite matrix. And then B is the average. That's good enough. The only thing that's different is now B is a vector. And S now is this outer product of these Y's. So S is a matrix in this case, okay? And by the way, S here is a positive definite matrix. Well, at least it's a positive semi-definite matrix because it's got to be, and it's symmetric. Because if I take the transpose, of this, it's got to be this. It's equal to itself, and it's easy enough to prove that if you take the outer product of S with some matrix vector, so if you do X transpose X X, for all X, that's got to be greater than or equal to 0. Why? Because you'll take X transpose Y, so that'll be some number. So that'll be that number squared. So the sum of a bunch of squared numbers can't be negative, right? All right. So that's a positive semi-definite matrix. And now, okay, this is a little bit maybe surprising. You proved it though earlier in homework. In Torture's homework 2, homework 1, chapter 2. You proved that you could write the multivariate Gaussian distribution in this form. Okay, and this is why it's useful now. Because now in this form, you start moving the positions, you start moving the terms around, and it becomes pretty clear quickly that S and B are the natural sufficient statistics for this exponential distribution. This family of exponential distributions parameterized by the mean, mu, and the variance, and the standard, the covariance matrix R, okay? So what does that tell you? It says multivariate Gaussian distributions are exponential distributions, and that the sufficient statistic are B and S here. The sufficient statistic isn't unique, so there might be other ways of expressing the sufficient statistic. For example, if you multiply these by some constant like 2, it would still be a sufficient statistic, but that's a sufficient statistic. Okay? Now, what's also kind of interesting is, okay, so, okay, this is, it doesn't say what this is. So when you take a random variable x, you have a sequence of excuse me, I promise I don't have a coronavirus, it's just chalk. Then, if you have a sequence of x's in time, each x takes on a discrete value between 0 and n minus 1, and the probability of it being equal to some particular value I is pi I, okay? That's called a multinomial distribution, I believe. Is that correct? Because sometimes I get confused about these names. Okay, so it's a multinomial distribution. Now here's the thing that's kind of interesting. Turns out multinomial distribution is also an exponential distribution. I can write the probability of the sequence as in this form, where the n's are the sums of the number of samples that fall into class M. And the reason is I can write it as the product of for each pi. Basically, for each probability, it's like you're counting events, right? So you counted the number of times class 1 occurred. So let's say it occurred 10 times, and then you take the probability of class 1, raise it to the power 10. And you do that for every class, multiply them together. That's going to give you the probability of the sequence, because it's the probability of each event in the sequence. And then, so if I take the log of that, I get it turns it into a sum. So it looks like this. And, okay, so then the maximum likelihood estimate is what we all know. This is polling, right? This is polling, which is particularly appropriate for this time of year, because you count the number of people who like vanilla ice cream, divide it by the total number of people, and then you get the rate at which vanilla ice cream lovers occur, right? Indiana's for vanilla ice cream lovers. So this is a fractional number you get here, okay? And, okay, right. So that's all good. And I think, yeah, okay, so now in this form, n is the sufficient statistic. So this n here is the natural sufficient statistic for the exponential distribution. So if you have a multinomial distribution, which is like polling, right? So we have 17, did Baskin-Robbins still have 72 flavors of ice cream or something like that? Okay, so Baskin-Robbins has 72 flavors of ice cream. You have 1,000 students. For each student, you ask them which flavor of ice cream they like the best, okay? Then what happens is that you count the number of students who like each of the ice cream flavors the best. Count the number of vanilla, chocolate, all the way to the end of 72. For each class, you get a number, an integer, n sub m. If you divide that n sub m by n, 1,000 in this case, it gives you the rate, it gives you an estimate of the probability of liking that flavor, right? So the n sub m, what people call the histogram, that histogram is the natural sufficient statistic for the multinomial distribution, or the family of multinomial distributions parameterized by the probability rates, pi's, okay? The pi's are the parameters, the n's are the natural sufficient statistics, okay? Is everyone clear on that? And because it's a natural sufficient statistic, you can express the maximum likelihood estimate in terms of it. What do? You just divide the number of people by the total, okay? And it gives, this is the common sense thing any normal person would do, okay? If they know how to divide. Now here's an interesting case. This gets a little trickier. This is how I do this in this course. It always starts off simpler and it keeps getting worse, okay? Now what happens is we have the x's and the y's occur in pairs. So you have a y and you have an x. The x is a discrete class. It's a multinomial distribution, right? So it's like the probability, it's like the ice cream flavor you like best for each person. But then instead of just, in order to make things more complicated, what'll happen is rather than me just tell you which ice cream I like best, instead I emit a multivariate Gaussian random variable with some mean and variance, and you have to guess. It's like some kind of alien race from a distant planet who comes here and goes, okay, and they emit this Gaussian random variable, and you have to guess. You have to guess what label I have. So now this is the Gaussian mixture distribution. So now what will happen in this case is that, okay, the x's are independent, identically distributed, so you're good there. But the y's are a little more complicated. The y's are conditionally independent given the x's. Right? They're conditionally independent. So if you know the x's, then they're independent. Okay? If you know the x's, they're independent, and their conditional distribution is conditionally normal with mean, not just mu and sigma r, it's mu sub. Is there a mistake in these notes? Oh, no, that's right. Mu sub m, but m here is x sub n. Because x contains the label of the nth sample. Are you lost by now? Okay. I know it's confusing, right? But once you get it, you go, oh, no, okay, it's not that complicated, really, okay? So that's fine. So you believe that equation. And then, okay, so here's the thing that's kind of interesting. So now, if you consider that sort of pairs of random variables, that's a distribution. It doesn't actually have a name. It's like we'll call it a Charlie Bowman distribution, okay? So it's got the multinomial x's, but the y's are conditionally Gaussian based on the x's. That distribution of the joint random variables is exponential. I'm not going to prove it, but you can work through. It's just rearranging the terms in the same way you did it before, okay? It's exponential, and what are the natural sufficient statistics? The natural sufficient statistics are n, b, and s, right? So what's n? And by the way, here we're assuming we know x and we know y. We've observed them. It's all observed. There's no incomplete data. We see it all. We see the x and we see the y. So for the x, we get the histograms, which is the n's. For the bm, we now have a different b for each class. And we have a different s for each class. Okay? Okay, the magic is coming soon, and when the magic comes, it's going to be powerful magic, okay? If we had the complete data problem, so all the data was observed, we could compute the maximum likelihood estimate. It would be easy as pie, okay? What we would do is, the estimate for the rate of occurrence is this. This is how many people like vanilla ice cream, the rate at which vanilla ice cream people occur, right? For each class, we do this, okay? It's straightforward. There's no partial membership here. We just take the BM divided by this corresponding thing. It's all good, okay? But then what happens when it's incomplete? What happens when it's incomplete? Here's the powerful magic. Okay, EM for exponential distributions. Here's the powerful magic. Okay, if it's an exponential distribution, it has this form. That was the assumption of an exponential distribution. It has this form. Keep your eyes open, because the magic is going to occur very powerfully and very shortly, and you blink your eyes and it'll go past, okay? So for the maximum likelihood estimate, we had some function of t, all right? Now, here's the thing, but for the Q function, this is the Q function. We have to maximize the Q function, right? So what happens is this. Okay, I think this. So what happens is this. Okay, it's an exponential distribution, so it has to have the assumed form, right? So if you take the log of the exponential distribution, you get this. But this is a linear inner product, and we're taking the exponential. That's the key. Because inner products are linear, so when not exponential, we're taking the expectation. Expectations are linear. We can take the expectation in the inner product. That's the magic is here to here, okay? That's the powerful magic. Everything else was just setting up the magic, okay? It was a long story, but all the power just occurred when I went from here to here, okay? I interchanged the expectation in the inner product. When I do that, it says, oh, guess what? The Q function looks just like the normal thing, except for the sufficient statistic has been replaced with its expected value. Right? If I just took that little bar, I'd get this irregular maximum likelihood estimate. But I just take the expected values of the t's. And that's the power. There goes the magic, okay? So what it says is that, okay, when you do an updated Q function, the only thing that's different is you, instead of using the maximum likelihood estimator, you just take the expectation of the natural sufficient statistics. So here's what happens, okay? So what happens is this. When you're doing the EM algorithm, I love to do this little piece here. It's one of my favorite things, okay? So when you're doing the EM algorithm, what normally happens is that, so this tells you the trick in doing the EM algorithm. When you're doing the EM algorithm, we have enough time, right? Oh shit, we're out of time, okay? But I just have to write this because this is the punchline. This is what you've all been waiting for, okay? So what happens is you have pi hat goes to m goes to nm over nm over n, and this goes to mu m hat goes to b over m over nm, okay? And then r hat goes to sm over n minus bm transpose bm over nm squared. Oh, this thing here has to do with subtracting the mean off, okay? So, okay, but this is correct for the complete data. If we have the incomplete data, we want to do the EM algorithm update. What do? Okay, we have to derive the new equations. Before, it was pages and pages of computation, right? Okay, now I'm going to do the calculation for the EM update. Are you ready? I just put little bars over here. You just put a bar over each of these, and you're done. Okay, you want to see that again? Okay. Okay, so this is the regular update for this is the maximum likelihood estimator. Now I'm going to do the EM update. You ready? Go like this. This is one of my favorite topics in the class. All you have to do is just put those little bars and you're done. Okay? So rather than have to do all those calculations, you just put those little bars over here. Okay? So if you have an exponential distribution, the EM update algorithm is really simple to derive. You just take the expected value of the natural sufficient statistic, where the expectation is over the posterior distribution of x. And then that's your update. And it's really pretty, okay? So in the particular case, I don't know, yeah, I think this is done basically. I'm done. So that's it. And then, so this is the EM update algorithm, and this shows you how you actually compute these things you saw. That's the E step, that's easy. And then this is the M step, okay? You're done, good. So that's it, and I think with that, we're finished the EM algorithm, and that'll actually work out nicely, because we'll just start with the Markov chains next lecture, and then we'll do hidden Markov models, and we'll do hopefully stochastic sampling. That may be all we'll really get done this semester, and I think that's fine, because that's mostly what's important. Okay? So take care, and I'll see you on Friday. Bye.